Welcome back to The Explainer. I'm absolutely thrilled you're here today because we're looking at something that honestly fundamentally changes how we think about AI context management. If you build with AI, you already know that managing an agent's long-term memory is basically one of the hardest challenges out there. Well, today we are unpacking an incredible open-source project called MFlow. It's a bio-inspired cognitive memory engine that completely replaces traditional vector similarity scoring with something way more powerful: path cost retrieval. And best of all, we're going to look at exactly how to plug this directly into your IDE using the Model Context Protocol, or MCP, with Claude Code.
But hey, before we get to the solution, we've got to talk about the elephant in the room. Why does standard RAG, retrieval augmented generation, just keep getting the context wrong? We've all been there, right? You ask your AI agent a highly specific question, and it returns this useless, fragmented chunk of text that just happens to share a few keywords with your prompt, totally missing the actual answer. It's pretty much a universal developer frustration at this point.
Okay, let's dive into this. Here is our roadmap for today. 1. The standard RAG problem. 2. Enter the cone graph. 3. Path cost retrieval explained. 4. The Claude Code MCP setup. And 5. Performance and limitations. Kicking things off with Section 1, the standard RAG problem, and why vector similarity fails.
So, standard RAG retrieves context based on vector distance. It embeds your query, ranks chunks of text by cosine similarity, and feeds the top results right to the LLM. It is essentially matching words like a dictionary. It's just looking for space proximity. LMFlow, on the other hand, retrieves by relevance. It operates much more like a cognitive engine, tracing coherent paths of evidence. And the core distinction here is absolutely crucial. Similarity and relevance are not the same thing. Similarity is just proximity in embedding space. Relevance is whether the system can actually connect your query to the answer through a logical structure.
To really ground this abstract concept, let's look at a fantastic concrete example right from the documentation. Imagine you query your agent with this specific question: why was Maria upset at Monday's stand-up? If you feed that query into standard RAG, the retriever immediately sees the words upset and stand-up. Because it's purely looking for high keyword overlap, it surfaces these generic documents about, how to run effective daily stand-ups or handling team conflict. It completely misses the actual cause, which is that Maria was blindsided by a deadline change over the weekend. That real answer lives in a totally different document that shares way fewer surface-level tokens. This brilliantly illustrates the exact failure mode of retrieving by vector distance instead of structural understanding. It just grabs what looks similar, not what is actually relevant.
Which leads us perfectly into Section 2. Enter the cone graph, our cognitive memory engine.
So MLflow actually organizes all of its ingested knowledge into a 4-level directed graph that forms this sort of inverted cone. Let's walk through these layers. At the very broad base of the cone, you have the episode. This is a bounded semantic unit, like an incident, a decision, or an event. Below that is the facet, which is a thematic dimension of that episode. Further down, at the sharp tip, you've got facet points. These are your specific atomic facts or claims, and cutting across all of this whole structure are entities, named people, tools, or concepts.
Now here's where it gets a little counterintuitive. In a traditional system, you might browse top-down, right? Narrowing your scope as you go. But in MFlow, a query actually enters at the sharp tip, hitting a highly specific facet point or entity, simply because those are the easiest things to match precisely with vectors. Then, it propagates downward through the graph to the broad base, gathering all that complete context. So the system ultimately returns a full, coherent episode bundle, not just some fragmented chunk of text.
Moving on to Section 3, Path Cost Retrieval Explained, or how we actually score this graph.
The entire design philosophy of MoFlow is pretty much captured in this single quote from the docs. One strong chain of evidence is enough. Think about how human memory works for a second. You don't recall a memory because every single detail points to it. You recall it because one single association triggers the whole thought. MoFlow mirrors this exactly. It looks for the minimum cost path to an answer rather than just averaging out the similarity of a bunch of random chunks.
Which brings us to the formal definition. Path cost retrieval is the process of scoring relevance based on the strongest chain of evidence connecting a query to an answer. When a query hits an anchor down at the tip of the cone, the system evaluates all the possible paths through the graph to reach an episode bundle. And here is the real kicker. The edges connecting these nodes aren't just structural links, they actually carry natural language meaning. They act as semantic filters. So if an edge is irrelevant to your query, it adds a high cost, essentially blocking that path from being retrieved.
Now, get ready for this because it's probably the most fascinating, counterintuitive logic in the entire system. The rule is penalize the most direct hit. I mean, why on earth would you ever want to penalize a direct match?
While penalizing a direct hit to an episode summary is a very deliberate strategy to filter out noise, episode summaries are by nature broad generalizations. If you search for project management, a vague summary about a project will absolutely be a direct hit, but it's broad, it's unfocused. By penalizing it, MFlow strongly prefers a precise path that starts at a specific fact, a facet point, and traces its way all the way up to the episode. This brilliantly prevents documents that simply look relevant from beating out the documents that actually have the specific evidence you need.
All right, let's get practical with Section 4, the Claude Code MCP setup, and connecting this to your agent.
The repository actually ships with an MFlow MCP subdirectory that acts as a tool server. To get this running in your IDE, the pipeline is super straightforward, though it does require Docker and Python. First, you just clone the repo. Second, you set up your .env file with your LLM API keys in your database config. Finally, you connect it to Claude Code using the command claude mcp add mflow pointing right to the Python module. Bam! This instantly gives Claude access to your cone graph. And once it's connected, Claude Code gets a suite of really powerful tools. The key ones are search to find memories by natural language, save_interaction to store important conversation contexts or decisions, and query to ask questions grounded specifically in that memory graph. This means your agent isn't just mindlessly reading raw chunks anymore, it is directly interacting with a structured cognitive memory store.
Let's look at a realistic use case for a developer. Say you're on a long-running project where context naturally fragments over time, like months and months of architecture decision records. You ask Claude Code, why did we move off PostgreSQL for the event store?
If Claude was using standard RAG for this, it would blindly fetch chunks mentioning PostgreSQL and event store completely in isolation, totally losing the thread of the actual conversation. But with the MFlow MCP, the system anchors on the specific query, traces the facet point, and returns the complete episode bundle. It literally hands Claude the entire context, the original write amplification problem, the Kafka evaluation, and the final decision. Claude then composes its answer from a complete, coherent narrative rather than just a pile of broken text fragments. It's a real game changer.
Finally, Section 5, Performance and Limitations. Let's look at the real-world data. So what's really interesting here is how these theoretical claims actually translate into hard benchmark numbers. On the LOCOMO 10 benchmark, which specifically tests long context and multi-session capabilities, MFlow scores a really impressive 81.8% with an LLM judge. That is slightly edging out Cogni at 79.4% and massively outperforming MemZero, which sits way down at 50.4%. The path cost retrieval clearly pays dividends when it comes to accuracy.
But, we got to be totally objective about the friction here. Building a cognitive engine is not a simple pip install. The setup complexity is very real. You're going to need Docker, a database backend, and Alembic migrations. Furthermore, ingestion definitely has a higher overhead. Building a multi-layered cone graph takes significantly more processing power than just embedding flat text. And finally, the public documentation for the MCP interface is currently just a little bit sparse, so you might find yourself doing a developer's absolute favorite activity, reading the raw source code to perfectly tune your Claude Code integration.
Despite that setup friction, though, the conceptual leap here is absolutely undeniable. We are moving from databases that merely store text to cognitive engines that actually understand relationships. So, I want to leave you with this provocative thought as you design your next agent. Is your AI just matching words like a dictionary, or is it actually following the evidence like a mind? Thank you so much for joining me on The Explainer today, and I highly recommend diving into the Mind MFlow documentation to explore this whole shebang further.